I've put on the blackboard here the things we were doing last time. We began our study of stationary states that are not normalizable. These are scattering states. Momentum eigenstates were not normalizable, but now we have more interesting states that represent the solutions of the Schrödinger equation that are stationary states with some energy E. Because they are not normalizable, we cannot directly interpret any of these solutions as the behavior of a particle. I cannot tell you a story, okay, so this is a particle is coming, colliding, doing something. These are not normalizable states. So part of what we're going to be trying to do today is connect to the picture of wave packets and see how this is used to really calculate what would happen if you send in a particle into potential. Nevertheless, we wrote a solution that has roughly that interpretation, at least morally speaking. We think of a wave that is coming from the left, that's a e to the ikx t. Now, in order to have a wave, you would have to have time dependence, and this is a stationary solution, and there is some time dependence. There is the exponential of e to the minus I e t over h bar, where e is the energy. So this could be added here to produce the full stationary state psi of x and t, but we'll leave it understood. It's a common phase factor for both the solutions at x less than 0 and x greater than 0, because the whole solution represents a single solution. It's not like a solution on the left and a solution on the right. It's a single solution over all of x for a psi that has some definite energy. So we looked at the conditions of continuity of the wave function and continuity of the derivative of the wave function at x equals 0. Those were two conditions, and they gave you these expressions for the ratios of c over a and b over a. We could even imagine, since we can't normalize this, setting a equal to 1 and then calculating b and c from those numbers. We have two k's, a k and a k bar. The k is relevant to the wave function for x less than 0. The k bar is relevant for x greater than 0. And they have to be different because this represents the de Broglie wavelength, and the de Broglie wavelength encodes the momentum of the particle, and the momentum of the particle that we imagine here classically is different here, where this has this much kinetic energy, and in the region on the right where the particle only has a much smaller kinetic energy. So that's represented by k bar, and k bar being the energy proportional to the energy minus v naught, while k squared has just the energy, is smaller than k. So this is what we did. We essentially solved the problem, and this qualifies as a solution, but we still haven't learned anything very interesting from it. We have to understand more what's going on. And one thing we can do is think of a particular limit. The limit, or the case, when E is equal to V naught, exactly equal to V naught, what happens? Well, K bar would be equal to 0. And if k bar is equal to 0, you're going to have just the constant c in here. But if k bar is equal to 0, first b is equal to a, because then it's k over k. So b is equal to a. And c is equal to 2a. And the solution would become psi of x equals, well, a is equal to b, so this is twice a times the cosine of kx, when a is equal to b, is a common factor, call it a, and this thing is the sum of two exponentials with opposite signs. That gives you the cosine. And for c, you have 2a. And since k bar is equal to 0, well, it's just 2a. It's a number. This is unnormalizable, but even the original solution is unnormalizable, so we wouldn't worry too much about it. So how does that look? For x over here, you have a cosine of kx, so it's going to be doing this to the left. That's for x less than 0. And at this point, it goes like that, just flat, psi of x, and here is 2a. So there's nothing wrong with the solution in this case. It's kind of a little strange that it becomes a constant, but perfectly okay. What really helps you here is to find some conditions that express the conservation of probability. You see, you have a stationary state solution. Now, stationary states are funny states. They're not static states, completely static states. Like, for example, if you have a loop and you have a current that never changes in time, this is a stationary condition, even in electromagnetism. So what we imagine here is that we're going to have some current, probability current, that is coming from the left, and some of it maybe bounces back, and some of it goes forward. But essentially, if you think of the barrier, whatever you look a little to the left of the barrier and a little to the right of the barrier, whatever is coming in, say, must be going out there, because probability cannot increase in this region. It would be like saying that the particle suddenly acquires larger and larger probability to be in this portion of the graph. And that can't happen. So probability current gives you a way to quantify some of the things that are happening here. So probability current was J of x, which was h bar over m, imaginary part of psi star d psi dx. So let's compute the probability current. Let's compute for x less than 0. What is the probability current? J of x, we can call it the probability current on the left side. I would have to substitute the value of the wave function for x less than 0, which is the top line there, into this formula and see what is the current. In fact, I believe you've done that in an exercise some time ago. And as you can imagine, the current is proportional to the modulus of a squared, the length of a squared, the length of b squared also enters. And the funny thing is, between those two waves, one that is going to the right and one that is going to the left, that's very visible in the current. This is h bar k over m, a squared minus b squared. It's a short computation. It might be okay and a good idea to do it again. It was done in the homework. And x greater than 0, j right of x, would be equal to h bar k bar. Now that, you can almost do it in your head. This c e to the I k bar x, look what's happening. From psi star, you get a c star. From psi, you get a c, so that's going to be a c squared. The phase is going to cancel between the one here and the one on psi. But the derivative will bring down an ik bar, and the imaginary part of that is just k bar. So the answer is this. And these are the two currents. Now, if we are doing things correctly, the two currents should be the same. Whatever current exists to the left, say a positive current that is coming in, to the right, it must be the same. Another pleasant thing is that this current doesn't depend on the value of x as x is less than 0, nor on the value of x when x is greater than 0. And that's good for conservation. It would be pretty bad as well if you look at two places for x less than 0, and you find that the current is not the same. So where is it accumulating? What's going on? So the independence of these things from x, this is constant, and a constant is very important because these constants should be the same. Now, whether or not you know about current conservation, it's encoded in Schrödinger's equation. And we solve Schrödinger equation. That's how we got these relations between B, A, and C. So it better be that these two things are the same. So JL squared, JL, for example, I won't put of x because it's just clear. It doesn't depend on x. 1 minus b over a squared. I'm starting to manipulate the left one and see if indeed the currents are the same. And now I get h bar k over m, 1 minus b over a squared. You know, I put the modulus square, but so far everything is real in this k, k bar, b, a, c, all real. Is that right? No complex numbers there, so I don't have to be that careful. B over a squared is k minus k bar over k plus k bar squared, a squared. Can I fit that here? Maybe. H bar k over m. Now what? This is squared, so the sum squared passes here to the numerator minus the difference squared. That's going to be a 4k k bar over k plus k bar squared, a squared. And yes, this seems to be working quite well. Flip this case, these two k's, flip them around. So the answer for JL so far is h bar, now k bar, because I flipped that, m. And now I would have 4k squared over this thing, which is 2k over k plus k bar squared, a squared. And this quantity, if I remember right, is just c squared, as you can see from there. So indeed, this is J right, and it worked out. This is J right. So J left is equal to J right by current conservation. So that's nice. That's another way of getting insight into these coefficients. And it's the kind of thing that makes you feel there's no chance you got this wrong. It all works well.